This theorem answered one question. Okay. Model, how can you know that model is model the n scenarios? How can I know that? Then I would like to write quickly.
Sir, the third term को equivalent इंजीनियरिंग सर उसका क्या फायदा था? Last term मतलब risk neutral property.
It's like if it's a good condition actually that by looking at just model you can know immediately that whether you are able to find a risk neutral probability measure or not. Because if you have risk neutral probability measure, you have the prices of the derivatives. So isn't that a good sign actually that just look at the model, just check 2-3 values, compare them, and this is going to guarantee that yes, there is risk neutral probability. Okay. Second fundamental theorem of asset pricing. Okay. So imagine we have previous model. And this theorem is going to tell you that, I mean, if you see the research basically in this area, people who are working in this area, they usually prefer binomial models. More than 2 scenario effect. And the reason is this beautiful theorem. Can you see this? So imagine I have a viable model. Model is viable, there is no arbitrage opportunity. I do not have a viable model. Following an equivalent. Number 1, model is complete. Price all derivatives. Second, so if the model is viable, from first fundamental theorem of asset pricing, we know that there is a risk neutral probability measure. Okay. The second property is that this Q is unique. The model is complete. Okay, this Q is going to be an excellent Q because it's going to give you the unique prices of the derivative or something like that. Okay. And the third condition is, but for getting all that, you need to have an input. If you have more than 2, that you don't have unique distinctive properties. Okay. Now, how can I quickly prove it? Okay. Just give me a sketch. So, why this is true? These both are true actually. You've done it already. In this chapter. That and it's true. And you must be unique to complete that. The only thing is going to be interesting is going to do that again when the converse is true. Okay. And for the converse, I'm going to argue contrapositively. I'm going to say that imagine I don't have this. And I'm going to say that I can't have this and I can't have this. Okay. So my argument is that I want to show that one implies three. Okay. My y is going to argue something positive. So suppose that n is bigger than 2, actually. Obviously it's going to be, it can't be less than 2. Okay. Then there is no randomness. Okay. N is bigger than 2. So if n is bigger than 2, then my claim is that market is not complete. So if the market is not complete, what I need to do? How can I show that market is not complete?
Take derivative.
Just find one derivative which you
cannot
can't
be
price.
priced.
Okay? And here is the derivative. Okay? Consider this derivative. So d1 of omega 1 is s1 of omega 2. So s1 of omega t is a number for me actually. Imagine I have a derivative which in the first scenario is going to give me the same value as this. And for the rest, so d of omega is s1 of omega for all omega does not equal omega 1. Okay? Claim is this, I can't price it. There's going to be no solution. Okay? Just check it. Check the full form. It's just okay, what you need to do is that imagine that you want to find a replicating portfolio x and y, and xb1 plus ys1 of omega equal s1 of omega 2. And then I have xb1 plus ys1 of omega 2 equal to s1 of omega 2 itself. And then you can have a third equation. You can have these three equations, and you can say, okay. So it says like you can have n equations, but only the first three are going to work. Sufficient to show that there is no solution. Just check that out. So your model is not complete. ठीक है जी?
Right.
So if n is bigger than 2, you can't have q unique actually. Why you can't have q unique? Because obviously you're going to have two equations. What is q? Q is doing what? It's doing two things. Number one, sum of qi is 1. Number two, sum of qi s1 bar of omega I is s0. Okay? And if n is bigger than 2, it's going to involve more than two variables. And hence you don't have a unique solution for that. And hence you don't have unique distribution property measured. We are saying that, okay, if you are saying that your model is viable, you have a Q. You have these two equations actually. But if the question is it going to be unique actually if n is bigger than? The answer is yes. The answer is that no, basically. Because, so for example, if n is 3, then sum of q1 plus q2 is q3 is 1. and then you're going to have
This quantity is
also going to, so you're going to have two equations and three variables, or maybe more than two variables, therefore you won't have this theorem. So I think it's something beautiful. Okay, but one thing which this theorem doesn't touch, if n is not 2, it doesn't mean that you can't price the derivatives. So just think about the first example. N was 3, but we know that there are derivatives which I can price, satisfies the condition actually. Yes, this payoff satisfies the condition. Okay. So this theorem is telling you that, okay, when you are not going to have n equal to 2, you're going to use, you're going to model the completeness. And people prefer this actually when they are modeling things and when they are trying to price the derivative. Why? Because they know that when n is 2, there is a price actually for the derivative. No matter what happens, I can find a price actually. But if n is bigger than 2, the trouble is going to be that you're going to solve the two problems. Number one, is there a price for the derivative? Second, if it is, what is it actually? Okay. But n is 2, there is a price. One problem is solved. The only thing is going to be that how to price. That's what it is. That's a price. Okay. So we answered the question. Third question. Second is still there. Okay. So if you wish, I can just give you a bigger picture. Okay. And then you can read the rest of the chapters. We spent lots of time on today recalling what we did previously. I'm not going to do this next time. Okay? Right. Let me just throw the last thing at you. Okay? So I'm going to tell you that how to price those derivatives which can be attained. Because I'm not getting into those which are not attainable. Okay? We're going to do this next time. For attainable derivative, you don't need to do something too much bigger. And you already see that how the very fundamental mathematics actually is occupying the territory in different sciences. One of the sciences is finance. And this is nightmare for people, especially here in Pakistan. People are not ready to get with this. So what I have covered, for example, with you in 2 lectures, last time I covered this in around 8 lectures actually. So just really slow actually to finance people with us. And for them, this argumentation was, so my emphasis was that, okay, let us not use anything which we haven't justified. You need to know the reason. Okay, using formula, they're using results. I can tell you that, okay, so it's like that's what is key thing is to price basically. So they said this is sufficient, we don't need anything else. Okay? So some programmer can make this programming which can calculate Q for me. Okay. I don't need to work hard for computing the prices, so I'm not interested in that. But at least we should see that why these things are beautiful and why they are connected. Okay, so how to price attainable derivative? And keep in view, I'm not assuming that n is true. N is general. Okay? I know that in general models, there can be derivatives which you can price, and there can be derivatives which you can't price uniquely yet. We can find the prices, but it's not going to be unique. Okay. What do you mean by an attainable derivative? How can I price that? So imagine I have a derivative d of omega. Okay. Omega can be anything. And I'm lucky enough. Okay. Just think about it. I'm lucky enough to find a single portfolio XY which can replicate this d omega in all cases. Just think about it. So for every omega, I'm going to have one equation in two variables. So I have n equations in two variables. And I'm saying we are lucky enough that all those, are meeting at a point actually. Imagine if we have this miraculous kind of portfolio. Okay. So if this is the case, okay, then we have also here law of one price, which can be proved by precisely same argumentation. And you can show that if this is the case, the pi for this d should be the v naught of the pi. That's pi. The argumentation is same. I'm not repeating the argumentation. The previous proof will work. So that's pricing through risk neutral replicating portfolio. Okay. And what is going to be the risk neutral measure way to do it? Okay. Imagine I have a viable model. Okay. And I have a derivative. Okay. For which I have been given some payoff. Okay. Give some payoff. So our first task is going to be find Q. But we know that Q is there because the model is viable. Yes, that's from that. Okay. Now, if Q is there, then how can I compute the fair price of it? The fair price of this, I can again prove that the Q of d bar is going to be what? So I can prove this theorem that since the model is viable, okay, I'm going to get Q, and using this risk neutral probability measure, if I compute the conditional expectation of d bar, let's go through. It's the precisely same argument that we had previously. The only thing that which kind of concerns you is this, that this Q is going to be for the one particular lambda, for example, in the first case. Okay. What if, so like, I know that my model is viable. Okay. So there is this little probability measure, but it's not necessarily unique actually. Okay. In other words, you can ask, is this pi well defined? In other words, is this pi is depending on Q actually? This choice of Q. Or is independent of choice of Q actually? The only concern is going to be that, okay, if I change Q, is it going to change pi? Pi or not? The answer is no actually. Answer is no. So that's a happy news. Okay. That's a happy news. And why this should be the case? Okay. Why this should be the case? This we favor of the model. There is a unique fair price. Okay. Tenable. Okay, if it is a tenable, then obviously Q is going to be unique. If it is going to be unique, then why it is going to be unique actually if I have if my derivative is tenable, it's going to be unique because of this fact. Why this fair price is going to be unique? This fair price is going to be unique because I have a unique portfolio which satisfies this condition. So it's going to satisfy what? This condition. And if this is true, and I discount both sides and take conditional expectation, I'm going to get basically what? The same value. So in other words, uniqueness of pi is inherited from here. Uniqueness of pi is inherited from here. Okay? The only thing that is going to kind of give you trouble is this that okay, what if I replace this q by some other q prime? The answer or the good news is that if you have two restricted probabilities measured, in case of a tenable derivative, not in general, we need to keep this thing in mind. EQ of d bar, EQ prime of d bar, they both must be equal. Okay. Read out this proof as well. That's a task for you. If you can do this, then actually we can go beyond. This is the next discussion. Okay. When are we meeting next?
Should I start it? Yes.